Well, I know we've all waited to hear from Dr. Baker, and so he has said moving from Solar Week will tie right in to, especially with all the activities that has been happening on the sun in the last few weeks, which has been really, really exciting. I love watching Facebook and seeing people hear on the news that there are solar storms, and then always followed up by the warning, be careful out there, friends. So I see it as a perfect opportunity to talk with my friends about what that really means and how it affects them. But I am really looking forward to this talk to be able to say more about what other things people can look for. So Dawn, do you want to introduce our guest?
Sure. I'm very excited to introduce this guest. Dr. Baker did a talk here at APL, and it was so interesting, and that I was really hoping that he would do it for us, and he has agreed. Thank you so much, Dr. Baker. Dr. Baker is the director of the Laboratory for Atmospheric and Space Physics at the University of Colorado in Boulder, where he is also professor of astrophysical and planetary sciences and professor of physics. His primary research interest is the study of plasma, physical, and energetic particle phenomena in planetary magnetospheres and in the Earth's vicinity. He conducts research in space instrument design, space physics data analysis, and magnetospheric modeling. Dr. Baker obtained his PhD degree with Dr. James Van Allen at the University of Iowa, followed by postdoctoral work at the California Institute of Technology with Edward C. Stone. He has held lead research positions in space plasma at Los Alamos National Laboratory and extraterrestrial physics at NASA's Goddard Space Flight Center. From 1994 until now, he has been at the University of Colorado. Dr. Baker has published over 750 refereed papers and has edited 8 books on the topic of space physics. He currently is an investigator on several NASA space missions, including Messenger, MMS, and my very favorite, Van Allen probes. He has won numerous awards for his research, education, and management accomplishments. And if you haven't already, I highly encourage you to see Dr. Baker's full bio, which Andy has posted on the WGO page. Welcome, Dr. Baker, and thank you so much for joining us today to share with us the possible societal impacts of a large solar storm.
Well, thank you very much for having me. And I'm going to try to bring up my PowerPoint presentation here, and let's see, I guess I'd like to share my screen. What do I have to do here to do that?
There should be a button at the bottom of your screen.
Yeah, let's see, is it the...
on my screen may look a little different than yours, but along the bottom there is a ribbon, and in the middle I have the word share screen, if you mouse over it.
No, that doesn't do it.
Are you on a Mac or a PC, Dr. Baker?
I'm on a PC.
You're on a PC. There's no ribbon at the bottom that has your microphone and audio and...
No, let's see.
No? Okay. So then go up to your...
Share screen. Let me do share screen here. And then
go up to your menu and you should be able to do it from there.
Let's see if we can do that. And then share screen only.
Hey, there it goes.
Okay, let's try this. Okay, let's see if that works. Maybe it's...
Looks good on our end.
Okay, good.
Yep, perfect.
Okay. So it's so easy, even a rocket scientist could do it. Okay, I'm going to talk to you tonight about extreme space weather and societal impacts. The slide you're looking at here was put together by NASA, probably by solar scientists, judging from the size of the sun. And I'd like to make the point with this opening graphic that we as developed societies and developing societies have really embedded ourselves in a cyber-electric cocoon. This cyber-electric cocoon extends from beneath the ocean surfaces with underwater cables, many technologies on the surface of the Earth that are susceptible to solar storms, the effects of solar storms, and of course, whole layers extending up through the atmosphere and into the Earth's extended magnetosphere, where satellites operate, that can be very severely impacted by solar storms. I'm going to try to talk to you about those things today, and I'd welcome questions if people have them as I go through this. This is a graphic I like to use, which really, again, I don't have to tell you, but other than the Earth being much too large relative to the Sun, and the Earth not being that close to the Sun, it's a perfect illustration of our Sun-Earth system. But the upper branch of this, if I can move my cursor, I don't know if I can, yeah. This upper branch is sort of the scientific branch that we like to study, understanding how the Sun works and understanding how that affects magnetospheres such as the region around our Earth, and then comparing that to other planets, and we're of course finding more planets all the time, and extending our knowledge onto the broad plasma universe. But the other branch, the lower branch, is really one that we're going to be discussing mostly tonight, and that's how this space environment can affect humans in space, how it can affect such things as satellite operations, power systems on the Earth's surface, communication, and possibly even affect the Earth's climate and hence contribute to climate change. So the definition, or a definition, of space weather is shown here. And this is from the U.S. National Space Weather Program, a strategic plan that was completed in June of 2010. But as you can read for yourself here, it talks about the many different kinds of ways that the space environment can affect technological systems, can endanger human life and health, and affect a wide panoply of different technologies on which we rely all the time. I often ask people to think about what would a day in their lives be like without the space segment, without the ability to have the satellites we rely on, the kind of information that we get from spacecraft, and all the other things where the space sector really touches our lives. And I think that's a very sobering thing when one thinks about it. So I hope my animation will play here, and it looks like it's coming up, but I don't have to tell all of you, since I just heard your discussion, that you understand very well that our Sun is our most important star in the universe, and how this star works is a matter of a great interest to us all. But of course, the space weather we're talking about in some sense begins with photons being generated at the center of the Sun in the nuclear furnace at the center, taking maybe 100,000 years to make their way out to the edge of the radiative zone. Then we have the outer part of the Sun, the outer quarter or so, that's known as the convective zone, and in this region, the roiling plasmas rotate at different speeds, faster at the equator, slower at the pole. That differential motion creates shears that generate strong magnetic fields. Magnetic fields are form what we would call a dynamo, and then that field can emerge. The upwelling and downwelling, the roiling, boiling surface of the Sun is fascinating in its own right. Sunspots from which strong magnetic fields emerge, and from these active regions on the Sun, we see many of the kinds of disturbances that we worry most about from a space weather standpoint. Beautiful data now from operating satellites, NASA satellites, seeing these huge prominences blast off into space. We see that there can be active regions, bands of active regions generating X-rays, strong magnetic fields emerging into these complex magnetic patterns, and ultimately leading to large expulsions of material, perhaps 10 billion tons of material moving out at 7 or 8 million miles an hour, constituting one of the real risks that the Earth faces from powerful solar storms. But of course, we have the X-rays that are generated from many of the active regions, and often these things emerge from with a flare like the one we just saw there, and then the subsequent coronal mass ejection makes its way at a slower pace, but nonetheless very fast out to the Earth's vicinity. So we have a lot of systems, and I'm going to talk to you about some of those systems that we have to observe this and to help provide forewarning to the citizens of the Earth about the sun and its activity. This is a slide that I like to show just to remind us that the sun undergoes approximately 11-year activity cycle, really a 22-year magnetic cycle, since the magnetic polarity flips during that 22-year cycle. But this is a series of snapshots taken in soft X-rays from the Yoko, a joint Japanese-US satellite, over an 11-year period, showing first the sun in its active phase and then quieting down to a very inactive state, and then coming back to the active state once again. I think it's fair to say that we don't know exactly why the sun has about an 11-year period. In fact, it's not very stably 11 years. It can be longer or shorter. Other suns, other stars like our sun, undergo activity cycles as well, but they can be quite different in period. And the Kepler spacecraft has been observing a lot of sun-like stars and seeing quite a range of behaviors. One thing that you probably are well aware of is that the sun has been, and sunspots as one measure of solar activity, have been traced now for over 400 years. Galileo first trained a satellite on the sun in the early 1600s, and in about the mid 1700s, the sunspot cycles, the 11-year cycles, started to be traced. The lower panel here in blue shows the numbered cycles. We are now in cycle 24. Of course, shortly after the sun spots were recognized and started to be studied, the sun became extremely quiet for a period of over 50 years. This was known as the Maunder minimum of solar activity. There have been other periods of relative quiescence. Interestingly enough, just a few years ago, in 2007, 8, 9, our sun became extraordinarily quiet. The solar minimum that the sun went through was among the deepest and longest minima that have been seen. And the top panel from our colleague Ron Turner overplots from 2 years before to 2 years after the solar minimum for the many cycles that are shown in blue there, and just puts the 2007 to 2010 minimum into perspective. And it was about as quiet as the sun was about 200 years ago during the dawn minimum. So the sun, every time we think we understand what the sun's going to do, it tends to throw something different at us. And so it's rather difficult to predict exactly what's going to happen. But just say 4 or 5 years before that deep minimum, the sun was extraordinarily active. This is from the famous Halloween storm period in late October 2003. And it's a sequence of images from the SOHO spacecraft. And first you see here the flare that occurs in the active region. And then there is noise, snow that appears in the picture. These are the very prompt energetic particles produced in the solar active region. And then this telescoping picture of the complete sun is from a chronograph measurements from the SOHO spacecraft, and shows this blast of material coming out pretty symmetrically. And so this is what we call a halo coronal mass ejection. And this is coming straight at the Earth. And these storms in late October were truly immense and caused a huge number of technical problems for systems back in that time. The next image that I hope will come up here, yes, is more of an artist's concept for the kind of space weather that we most are concerned about, and it is these coronal mass ejections. As I noted, these lift off from the sun quite often at high speed. A little later, I'll talk to you about one of the recent ones that is really amazing. This one, this illustration shows this 10 billion ton blast of material coming out. If the magnetic fields within the cloud of material are the right form, they can open the gate of the Earth's magnetosphere, can impart huge amounts of energy to the system, and can lead ultimately to bright aurora, powerful geomagnetic storms, and immense effects on all the kinds of technologies that we were talking about before. just to put this into some context, this region around the Earth hosts a wide range of different spacecraft, and of course the atmospheric and ground-based systems that can be susceptible. Just one illustration of this is the huge number of satellites that are out at the geostationary orbit at 6.6 Earth radii from the center of the Earth. And these fill almost every available niche around the geostationary band. And this is probably an outdated estimate now, but there are several $100 billion worth of space assets just in these civilian satellites at geostationary, all of them being possibly susceptible to the space radiation. So a few years ago, now I guess a decade or more ago, in Science magazine put together a perspective about space weather, and this diagram from that just makes the point that solar disturbances can come out and affect the environment around the Earth as well as the Earth itself. The kinds of things that we worry about for space systems include the effects of high energy particles, the kinds of things that cause the snow in the picture that I showed you before, can also cause enhancements in the radiation belts, and of course I will talk about that. Also can cause surface charging on spacecraft. And the high energy ion effects can include memory upsets, degradation of solar panels, and a wide variety of things. But just one graphic illustration of the effect is this one. In the active period of the sun in the year 2000, there was a powerful storm then, too, that was called the Bastille Day event. And this storm, this is a picture, a beautiful ultraviolet image of the sun taken early on the 14th of July. Just about 6.5 hours later, that same picture looked like this. This is now, again, the blinding of the CCD camera by the high energy particles from the sun. So before and after. It doesn't take a lot of imagination to to think about human and space, human eye, human brain being subjected to this huge barrage of extremely high energy particles. And of course, every system in space becomes an energetic particle detector, whether it wants to be or not. And this is really a very substantial part of the risk to human systems. The other thing I'll talk about, and Dawn mentioned one of my favorite missions too, the Van Allen probe's mission, which has been measuring the radiation belt environment, these high energy electrons that can bury themselves in dielectric material. And this illustrates the idea there that under normal circumstances, high energy electrons in space from the Van Allen belt, say, can pass through the spacecraft shielding, can bury themselves in insulator material, but they will leak out and reach some kind of equilibrium and generally not cause severe problems. But if the buildup is fast enough and strong enough, it can lead to a small electrical discharge inside of sensitive electronics. This can damage in very substantial ways the electronic pathways, can cause failures of systems. And this has led to many satellite losses or anomalies. And for example, the Annex satellites that were, these are the Canadian satellites that lost control in the 1990s. And we studied this in considerable detail. Is someone trying to reach me? Okay, good. Okay, so the modern, as we've moved from the beginning of the space age to the present time, there are many new technologies that are substantially affected by space weather. So there are many new drivers of need for space weather forecasts, and this just lists some of them. I'm sure many of you use the global positioning, global navigation systems, GNSS, general term. The next generation air transportation system is going to be very aware of and dependent on knowledge of the space weather situation. We're going to talk more about the vulnerability of the power grid to space weather, commercial space industry, and of course human exploration and so on. Many different areas, increasingly significant concerns about space environment and space weather effects. This is a somewhat old diagram. I just show it because it was quite an underestimate, but this was made back in the mid 2005 period or so, about the growth of the use of the global positioning satellite system. It's used in a wide variety of ways, as we'll talk about. You well know that there are a constellation of 28 active spacecraft that fly at about 4 Earth radii above from the center of the Earth. And the estimates were that this would grow by some substantial amount by present time. Well, we've really exceeded this. This is a multi-trillion-dollar kind of system now. It's, the business that relies on GPS is just staggering. And of course, it's used for positioning, for surveying, for construction purposes, seismic data collection, and a whole host of other things, precision agriculture. And we are building more and more dependence all the time on the timing signals as well as the navigation signal used for the GPS program. And space weather can affect this in quite a variety of ways. Of course, there can be direct effects on the global positioning satellites, but there can also be effects, scintillations that are generated. There are regions in the ionosphere that cause scintillations for radio signals. And so the ranging, where we depend on centimeter kind of accuracy for being able to range systems using GPS, can be substantially disrupted and can, in fact, be really severely impacted by the space weather effects. And one of the hopes had been that this GPS could be used to sort of eliminate the need for the ground-based navigation systems that airlines relied on, as illustrated here. So the idea was that GPS could supplant this. But so the wide area augmentation system, which was being tested back in the Halloween storm period, here in this animation, blue is good, red is bad. This is really an illustration of the total ionospheric electron content. And over the course of this period of time, just in a few hours' time, the system went from blue to totally red, meaning that the system was essentially unusable. And this persisted for, I think, about 30 hours or so, that the GPS precision ranging for WAS really was lost because of the storm activity. And so this caused a real rethinking of how one would be able to use GPS under extreme storm conditions. The next diagram that I hope will come up here, yes, this is another impact for airlines. So airlines seem to have a lot of issues, and this is a diagram that makes the point that one isn't just waiting around for coronal mass ejections to reach the Earth. If there's a powerful X-ray storm of the solar flare that we talked about earlier, that flare can cause intense ionization on the sunward side, on the day side of the Earth, affecting essentially the entire hemisphere. And this can cause the change in frequencies that can be used. High frequency and very high frequency radio communication can be knocked out or can be substantially altered. And so this can be effects that last for several hours or the better part of the day, and there can be quite a bit of disruption. And of course, we, in many systems, military and civilian systems, rely on HF communication, and this can be disrupted quite substantially during solar flares. So that's a very prompt effect. One of the newer concerns, of course, revolves around the fact that airlines now are flying much more extensively between North America and Asia, and are trying to find the most economical and fastest routes. And those now are the transpolar routes. And so airlines such as United Airlines fly a variety of pathways from Washington or Chicago to Asian destinations. And flying over the pole, the company rules, FAA rules, require that they be constantly in radio contact. This can be done with satellite communication below 82 degrees, but the yellow circle up there above those latitudes, they have to rely on HF communication again. And during storms such as the Halloween storm, the entire polar region acts as a funnel. High energy particles from the sun, the things that cause the blinding of the CCD cameras we talked about before, can burrow down, can funnel down into the north region. So you recognize the North Pole there, and that red region is the broad swath where high energy solar particles can cause, again, radio outages and basically obviate the ability to fly these polar routes. When airlines can't fly the polar routes, they have to fly lower latitude. They're usually bucking headwinds, and often this can lead to requirement that they add more fuel or stop along the way, or perhaps even cancel the flights if the radiation is intense enough and broadly distributed enough. So this is a new and very substantial concern for airlines. Human space flight, we probably don't need to dwell on this too much other than to say that, of course, have the International Space Station operating continuously with humans on board, and high energy particles from the sun, from solar storms, as well as enhancements of the electron radiation belt can cause concern, especially for extravehicular activity. And so this is a significant problem, but of course, if we're looking at even longer duration flights, let's say to Mars or so, then there will be months, many months of humans being out in free space, where solar storms can have a full impact on the vehicles. And so it was my privilege a number of years ago to chair this committee for the National Research Council for the National Academies to look at the space radiation hazards. And one of the charts from that listed some of the radiation risks that we are concerned about, causing cancer, of course, degenerative tissue effects on the heart, the lungs, the digestive system, damage to the central nervous system. All of these can be long-term as well as more acute risks. When it comes to acute risk, death is a bad one. Vomiting in a spacesuit for those who are out on a planetary surface can be definitely a life-threatening situation. And so the recognition that space radiation is a strongly limiting factor for human exploration is pretty well recognized, and this is probably one of the tall poles in the tent, as they say, about long-duration space flight. I was also asked to chair in 2008 a study that goes right to the heart of the topic of this lecture tonight, and that is the societal and economic impacts of severe space weather. We recognize that there had been many studies of the effects of earthquakes, floods, and other kinds of hazards, but that there had been relatively little done to try to assess broadly the economic and societal impacts of space weather in any integrated sense. So we brought together in a workshop setting representatives from academia, industry, government, and all of these different sectors, some of which we've talked about already, to try to do an econometric analysis of what the benefits, say, of better forecasts would be and so forth. And this report has had quite a shelf life. It's been translated into a number of different languages. I have the Chinese version, which I can't read, but I have this on my desk. And there have been many other countries that have used this as a springboard for doing their own assessment. But perhaps one of the most important figures from this study was really this one about the interdependencies of society. You probably all realize this, but you think about the cornerstone technologies such as electric power and how dependent everything else is on that. If you lose electric power, you quickly lose the ability to pump oil and gas, gasoline. You often lose communication, or at least the kind you normally depend on. Provision of potable water quickly ceases. Effects on banking and finance can be almost immediate. Significant effects on transportation, emergency services, the things that you probably most need at these times, government services. And whether it's space weather or tropospheric weather under certain circumstances of the type that we saw in Superstorm Sandy, for example. Things that knock out electrical power quickly cascade to affecting all aspects of modern technological life. And so this is an immense concern, and probably one of the biggest current concerns of the government about severe space weather events. Also in the report was a diagram from colleague John Kappeman, who had taken a particular storm. He chose to study a storm that occurred, was pretty well documented back in the 1920s, was a very, very powerful storm, and looked at if that storm were to occur today, how would this affect the extremely high voltage backbone of the electric power system in North America. And here the purplish and black lines show the kind of extremely high voltage backbone grid, and the red and green kind of circles represent where there would be very large geomagnetically induced currents that can burn out transformers and cause the loss of those transformers. Literally hundreds of transformers would be at risk here. These are house-sized transformers costing many tens of millions of dollars a piece, and if those are knocked out, they would take months or years to be replaced. And so this is a very substantial risk. And you know, imagine this sector, this entire eastern third of the United States that's circled there, being without power for weeks, months, or possibly years. It's really quite staggering to think about. So the fact that was discussed in the report was that the grid is becoming increasingly vulnerable to space weather effects. One of the reasons for this is that the system is operating closer and closer to the margins all the time, more and more reliance on electricity, and yet the infrastructure is not being updated and moved along as quickly as it probably should be. And so the geomagnetically induced currents can burn out the transformer windings, and overheating can cause meltdown. And this is really, as I said before, one of the big concerns. The question is, how big can these storms really be? And the documented, probably the most documented of the giant storms was an event that was actually the first solar flare ever witnessed by at least Western scientific eyes. Richard Carrington in 1859, in late August, early September, was looking at the sun, was mapping sunspots, sunspot groups, and saw a massive white light flare. We now recognize that that's what he saw. Over the period of the next few minutes or so, it flared up and then began to die down. Other colleagues of his had also seen this. They were also mapping the sun at the time. And over the next, in the next couple of days, there was a huge geomagnetic storm. And one measure of how broad the effects were was the fact that aurora were seen down to extremely low latitudes, seen down to Cuba in North America, as far north as Santiago in Chile in the southern hemisphere. The internet of that time, of that age, was, of the Victorian age, was the telegraph system, and this was severely affected. Fires actually broke out from the sparking of induced currents in the telegraph wires in many places. Many of the telegraph systems went off of batteries and just operated on the currents that were induced in the wires by the storm. People could read newspaper by auroral light in northeastern United States, and there are fascinating accounts of this in the New York Times and other places during this storm period. So this Carrington event, or this actually pair of events, has been held up as perhaps the kind of extreme case that we ought to be able to design to. Of course, we had very little knowledge of the sun in those days. We didn't have spacecraft observing the properties, and I'll touch on this in a second. But the low frequency, high consequence events, the increasing vulnerability of the power grid, this is somewhat garish. I apologize for the garish slide here, but it really repeats the point that the outages to the power grid could extend to periods of years and could be trillions of dollars of damage. And this kind of study that was cited in the Academy report has been repeated more recently by Lloyd's of London and largely validated. It differs in some detail, but the conclusion is that there could be substantial outages in North America or Europe or other highly developed places. So these large storms, these large geomagnetic storms that have been garnered most attention have not generally occurred during the most active solar cycles. The 1859 storm, what's plotted here is sunspot number, as you see, over as a function of time into the early 2000s. And the Carrington storm, the 1859 storm, occurred at just after the peak of what was not a particularly large or high sunspot number cycle. The 1921 storm that we just talked about from Kaufman was also a relatively modest activity cycle. And as I'll talk about in a bit, we have gone through now a pretty wimpy, some would say, solar cycle maximum, and yet we've seen some very powerful solar disturbances. Let me talk about that here now for a second. And this is a picture of the sun in July, taken from the Solar Dynamics Observatory, another magnificent solar observing platform that we have operating near Earth, looking at the sun. In this active region, again, if I can use my cursor here, just point to this very nasty looking active region, or beautiful depending on your point of view, was popping off powerful coronal mass ejections as it moved across the disk of the sun toward the Earth. But just about a week later or so, as the sun had rotated and as this active region had moved beyond the limb of the sun, the Stereo A spacecraft, which was around away from the Earthward direction, was able to observe the sun. And so at the center you see in ultraviolet the sun, and you see these nested coronagraphs. You see this huge blast of material that's reminiscent of what we looked at before, and the blinding effect of the charged particles. So we have studied this event and come to some, I think, significant conclusions. If you look at this, I'll ask you to just focus on the left side of the screen here. This is the top-down view. It's as if you're looking down from the pole of the sun down on the solar system. And again, if I can use my cursor, the yellow dot here is the Earth, and portrayed are some of the magnetic field lines that would be emanating from the sun. Almost everything we care about, Earth, Venus, Mars, many of the satellites of NASA are all aggregated over on this lower right quadrant. But over on this side, on the far side of the system here, we have the one spacecraft, the Stereo spacecraft, as the red square. This blast of material from the sun, the coronal mass ejection, moved out from the sun to the Stereo location in about 17.5 hours. This is absolutely as fast as the Carrington event of 1859. So we believe that this is very closely analogous to what the Carrington event was like. And if the Earth had been at the location of the Stereo spacecraft, which is about 1 AU, or said differently, if this event had occurred just a week earlier, the Earth would have been subjected to a Carrington-type event. And this is pretty sciencey here, but it really shows that stereo measurements allowed us to look at the magnetic field from the in the coronal mass ejection, look at the solar wind speed, look at the density. And we can run those kind of data through our models of what kind of geomagnetic storm would be generated. And in this figure, the red one is the largest storm in terms of this index called the DST index, a measure of geomagnetic storm activity. That's the largest storm that's been seen since the DST index has been generated since 1957. The largest storm of the 20th century was about 589 in these units. The July 2012 storm had it hit the Earth, would probably have produced something at least twice as large in that index, and at about 1,200 nanotesla. So it would have been by far the largest storm that we've ever seen, and we missed that by maybe a week or a few days. So this has led to a number of people like Ying Liu and others studying the event as well, getting a deeper understanding of what was going on there, and they concluded very similarly to us that this storm would have produced the largest DST by far that's ever been seen. They also made the important recognition that this was really two different coronal mass ejections in rapid succession. So this is a very slow-moving animation here, but it gives me a little chance to talk through this more, and it again labels a lot of the spacecraft so you can sort of get the picture. But this active region during a relatively modest solar activity cycle nonetheless is immensely active, powerful, popping off coronal mass ejections several times. The line moving across there shows that there was one coronal mass ejection that went out and sort of cleared out the system, and then this next one that's coming along moved out much more strongly, much faster. And so this kind of 1-2 punch where you have a disturbance, and then the second one can move out more or less unimpeded, can really lead to the most intense kind of geomagnetic storms. And this is what we really worry about. So what about addressing space weather? We are in a magnificent time now with the observations of the sun. We are seeing it from many different angles. We have this ability to study the drivers of space weather with unprecedented skill and unprecedented knowledge. We can see those. We have also in operation now many spacecraft systems in the Earth's vicinity. We can understand these impacts on the power grid. We're recognizing from many of the operating spacecraft that these nice cartoons we often show of the Earth's magnetosphere and its magnetic environment, nice laminar flow, really are not very accurate. The system is much more turbulent and disturbed than we previously thought. These kind of currents flowing down from space can be coupled into pipelines and power grid. They can cause the kind of outages that we've seen on more regional scales, like in 1989 in Quebec. These power outages are severe, but they can also be coupled then with the kind of loss of ground-to-ground ionospheric communication high frequency that we talked about. These can affect aircraft operation. Also, the transmission through the ionosphere, as we talked about, knocking out communication for things like GPS and ATMs and other kinds of things that we just have come to depend on. Of course, precision agriculture, navigation at sea can all be severely impacted in the ways we've talked about. And the operating spacecraft, the constellation as a whole can be affected. But individual spacecraft, either degradation of the solar panels or knocking out of electronics, all of these are worries. And ultimately, of course, the risk to humans in space is a substantial one. So we're fortunate to have many scientific satellites now that are giving us these wonderful views. But another study that I was privileged to lead, I guess I do a lot of studies for the NRC, but this is a very recent decadal survey, as it's called. This is every decade or so, the disciplines of solar and space, space science and earth science it's demanded by Congress that these disciplines do a self-evaluation of what are the most important issues, what are the things that should be pursued in the next decadal interval. And our report, released in 2012, covered the period 2013 to 2022. And our study about solar and space physics made the point that we have magnificent scientific tools at our disposal now, but that we really need a much more operational kind of space weather system. We've built our present space weather capability largely on the back of these scientific satellites that are not required to operate 24/7. They are not required to be replaced once they've run out of utility or that they fail. And the recommendation, the very strong recommendation in the decadal survey that we made was that we really need to use these scientific tools, yes, but we also need to have a national or truly an international space weather observing capability so that we can keep our eye on the sun and see the consequences in the Earth's vicinity. Many of these satellites that we see here do have real-time capability and are contributing right now to our space weather readiness, but we need to do better. The RBSP, or what was renamed in November 2012, the Van Allen probes, are one great example of this, where the spacecraft were built at the Johns Hopkins Applied Physics Laboratory. I was privileged to be a principal investigator on the Van Allen probes, and using the scientific data from these spacecraft, sort of the first thing right out of the box, we discovered that there are not just two Van Allen belts, but there can be a third ultra-relativistic electron belt on occasion. So this third belt was one of the early discoveries of the Van Allen probe's mission. And recognizing that, again, the things that we thought we knew so well can be different, can be quite different than we expected. And as Dawn recalls, I think I cited the great American philosopher Yogi Berra, who said you can observe a lot just by looking. And this ability to look at the system with new eyes was crucially important. So we have now the Van Allen probes joining a lot of other scientific satellites and some operational satellites that constitute an observatory fleet that's circling the Earth, giving us this unprecedented information about the earthward end of the Sun-Earth system, combined with what I think I've shown you before is the solar observing satellites, a magnificent set of tools. We've never had it so good, but as a society, we need to use all these assets, and we need to make sure that we continue to have these kinds of assets into the future in order to observe this connected Sun-Earth system that I spoke about before. So people often ask me, what do we do about this threat to the power grid? And in a little article in Space Weather Journal, I just reported on one kind of group that meets regularly now, the Electric Infrastructure Security Summit. And these points are pretty evident, I suppose, but one thing is that we really need to establish pretty clearly how bad can it get, and so identifying a worst case. And I believe that the case I showed you for July 2012 is a great start on this. That tells us how bad it can really get. We need to identify, as a society, the critical infrastructure. We can't protect everything or all facilities, but we maybe can identify the core technologies that have to be protected. Detailed modeling of the effects, go to step one here and take the worst case, and then war game this through and look at what the influence of this severe space weather would be on our present national power grid is a crucial step. And then finally, for accomplishing step two, identifying ways to block the effects of geomagnetically induced currents and to protect the key infrastructure is an obvious step that needs to be taken. And I think if these four steps were followed through assiduously, we could be a much safer society. So let me just conclude by saying that I believe that we have before us the ability to address and probably solve the space weather puzzle in many respects. We have space and ground observations. We need to add more. We need better models to take this information and turn it into knowledge and wisdom. With this complete forecasting capability and an ability to provide alerts and warnings, in addition to the kind of steps to protect key infrastructure, I think this is a soluble problem, but it's an expensive and requires tremendous commitment from policymakers and from scientists and from engineers. So to summarize, I'd say the challenges of space weather really do affect all developed and developing countries, both civilian and military systems. This work on space weather, specification, modeling, forecasting, I think has great societal benefits. So in many ways, I would say it's basic research with a high public purpose. Almost all future space exploration, of course, most modern human endeavors will require that we have a better, more capable understanding of, and transition more of our knowledge to operations. And one of the questions that may be in your mind is, how do we adequately deal with these threats without being unduly sensationalist? Maybe the question is how to be duly sensationalist and avoid this chicken little, the sky is falling syndrome, but still get policymakers to step up and recognize this as a significant threat. So thank you. I'd be happy to answer questions if there are any. Anyone there?
Sally, do you want to ask your question? I know you asked Claire, but I didn't know if you wanted to talk more about that.
Well, I was just wondering, does all this information help with predicting these storms so that they can be prepared?
Does this information help in predicting?
In predicting so that we can be prepared for whatever we you know, will encounter, blackouts or astronauts.
Yes, I think that knowing what the sun is doing, being able to see what the sun is doing, and being able to follow these kinds of the most significant of these disturbances out allows us to predict a substantial amount about what's going to happen. The predictions about the solar energetic particles and the arrival of the coronal mass ejections has been getting much better. One of the problems that we have with the coronal mass ejection story is that we don't know from looking at the sun alone what the orientation of the magnetic field is within this cloud of material, and not knowing that can turn an event either into the extreme, like the July 2012 event that we saw, or it can be pretty benign if the interplanetary field is in the wrong orientation. Effectively, if the field is pointed opposite to the Earth's field, that is southward directed in interplanetary space, the storm is going to be generally a very large one. If it's pointed northward, it's going to be more benign, and that's been the missing ingredient in our forecasting ability, is to really know how strong the magnetic field is and what its orientation is.
And has the coronal mass ejection affected the magnet, like its density? I know its shape, but does it like strip things away?
Yes.
Or
yes, it does. It compresses and distorts the magnetosphere very substantially. It can drive the normal outer boundary of the magnetosphere, which may be out around 10 or 12 Earth radii. That's been driven in as close as 3 or 4 Earth radii from the center of the Earth. So it massively compresses and distorts the system. And it can sort of strip away the outer layers of the protective magnetic envelope around the Earth for, you know, for a period of time. The Halloween storms, for example, caused a complete redistribution of the radiation belt particles around the Earth and caused caused the radiation belts to reform in places that simply hadn't seen high energy electrons for a very long time. And that's what caused a lot of the spacecraft operational anomalies that occurred during that storm period. By the way, these coronal mass ejections probably have played a very important role in other planetary systems. We have a new mission that's being run out of our lab in Colorado called MAVEN, a Mars mission. And MAVEN is at Mars right now, in orbit around Mars, went in orbit on the 21st of September. And it's going to be studying how these coronal mass ejections strip away the upper atmosphere of Mars. this probably contributed a lot to the ultimate loss of the atmosphere of Mars and the water from Mars. So these solar blasts really play a pretty important role in planetary atmosphere development.
Dan, can I just say that it's very interesting to hear the actual detail of how solar storms affect things like power grids. I guess, you know, in the solar community, we throw these terms around and these sort of end results around without really thinking them through. So it's been really interesting to hear the detail of where the actual damage happens, or what's the specific occurrence that causes this to be a problem. So thank you for that. That was very very insightful.
Thank you. Thank you. Yes, I think that we hear, you know, sort of broad assertions that the sun is active, and maybe until we think it through, we don't realize the many ways that that activity can manifest itself, or it can affect our systems. And not every solar storm, you know, is the same on all the different axes, on all the different things. You can have a storm that maybe is weak in terms of the solar energetic particles, but very strong in terms of the coronal mass ejection, plasma flows. In other cases, you might have a very, very strong X-ray flare, but the coronal mass ejection might go off in a direction that doesn't hit the Earth. All of these things are possible, and I suppose in many ways we worry most about the perfect solar storm, probably the kind that, again, the July 2012 event would have been had the Earth been in the wrong place, but where you've got the combination of strong flare followed by very strong enhancement of solar energetic particles, and then the blast of the coronal mass ejection getting there in such a short period of time that you would have very little time as a society to really prepare for the effects either. You know, going from the sun out to the Earth's orbit in 17 or 18 hours means that one would have less than probably half a day or something like that to even start to mobilize your defenses.
I've got a question that moves away from the electrical aspect and goes to the major, very large pipelines that are being constructed.
Yes.
We have one here in Alaska. It's 800 miles long.
Yep.
And large enough to carry over 1 million barrels of oil a day. When the Keystone Pipeline is going to get built, and it will get built, it's going to be way longer and much larger. What kind of ramifications would say a Carrington event have on those pipelines?
Yeah, it's a great question. Of course, as you well know, in Alaska, where the currents, the geomagnetic induced currents, are a much more regular phenomenon, there were very substantial problems with that, requiring special treatment grounding. Otherwise, these large currents could quickly sort of burn a hole in the pipe and cause massive damage, environmental damage, and so on. For the more mid-latitude pipelines, under, say, normal geomagnetic conditions, one might not worry so much about that. But as these much stronger storms occur, the activity tends to move down to lower latitudes, and these would become susceptible. So it would be a rarer but much more significant problem under the most extreme space weather conditions for that. And I think this has to be a very significant part of the planning process for any kind of long, whether it's wires or pipes or anything that can act as a collector of these geomagnetically induced currents over very vast distances. The potentials that can be generated in these storms is really huge. I mean, it can be thousands of volts, you know, tens of thousands of volts of potential difference, very strong currents flowing, and it doesn't take long to sort of eat their way through the most well-designed pipes. Very significant concern.
Thank you.
Yes.
Chris said he lost his audio, but
Okay.
he has a question. Is the ESA's solar orbiter mission still moving forward?
Yes, it is. We had briefings on that today, as a matter of fact, the meeting I was at, and it looks like it's moving toward a 2017 launch. Yes. NASA is providing, some instruments for that. I believe is providing the launch vehicle for that.
And there's actually some of the scientists from the Space Sciences Lab are helping with some of the instrumentation for STIX. They have joint positions between SSL and an institute in Switzerland, actually, and the PI for STIX is a researcher from SSL, so that's moving forward. It's going to be based on, for those of you who know RESI from back in the day, it's going to be based on RESI, but like an updated, much better, higher quality version of RESI.
Right.
And everybody just thinks the sun is a star, you know.
Well, it is. As I say, it's the most important star in our lives, at least. But it's been fascinating to be part of the Kepler program. We're doing the operations for Kepler at LASP, and seeing the data coming back from other sun-like stars, and seeing within that general description about the same size, about the same age. But there's tremendous variability from one sun to the next, and we see on some of the sun-like stars activity that is orders of magnitude greater than the sun's activity, and flares that are like 1,000 or 10,000 times as powerful as the flares that we see from our sun now. So it again begs the question of how large could these solar disturbances really be, and could we, how extreme can extreme events really become? And I think that's the challenge that many of us in the space weather business are really facing, as we get asked by policymakers, well, how bad could it be? And we really don't know the answer. We've been observing the sun effectively for a few decades, and we don't really know the answer to that question. And the sun's been operating for 4.5 billion years, and it's presumably done lots of things at that time.
So I have another question. You briefly said that the Kepler mission was seeing solar storms, sunspots on some of the stars that it was looking at.
Yes.
I know we haven't had enough time to build up our database on that yet, but are they seeing the bigger the star, the more sunspots, or vice versa? Or are they just now noticing that they're out there?
Well, of course, as you say, the database is there. These active stars are really an annoyance to the Kepler program. What they're trying to do is to look for the signature of planets moving across, and so having a quiet star so that the diminution of light can be done effectively for the planet is the sort of the norm. When you have a very active star or so, that sort of messes up that whole program. So in a sense, the normal Kepler folks would throw away or want to throw out the data from these more active stars. But there are, of course, many scientists who are really interested in studying this aspect of sun-like stars. And so that has now been, there are a number of Japanese scientists, a number of American scientists who have been really taking that database and running with it, and that looking at the most extreme of those helps to put our own sun into better perspective. And so this is the great benefit of comparative studies, whether it's comparative planetary or comparative solar stellar studies. I think the final word has yet to be written about this, but it's really stimulated a lot of thought about just how active our star could become.
Hi, this is Paul Higgins from Trinity College in Lockheed Martin, and I've heard a lot of talk over the last few years about long-term solar activity affecting Earth's climate, and I was just curious if you have any update on that, or have you seen any convincing research that that's the case? Because I do know that a lot of the climate scientists want the solar physicists to stay out of that, and that they're really sort of diluting some of the climate research.
Yeah,
I get that question a lot too, Paul. I really would like to hear the answer to that.
Yeah, no, it's a very good question, and indeed, let's say some climate scientists would rather not broaden the discussion too much, would not like to sort of reduce the noise level, and stay focused on the anthropogenic effects on climate. But I think that again, folks in our lab have now maintained this record for some 35 years or so of the solar variability, and the solar irradiance varies modestly, a few tenths of a % over the solar cycle, and that is the backdrop upon which human induced climate change effects are superimposed. So I think it's bad science not to study all the things that affect the atmosphere of the Earth. And of course, the record shows that prior to, say, 1950 or 1960, that almost all the variability of the Earth's atmosphere could be accounted for by the variation in the solar irradiance and other effects, volcanoes and things like that. I think the record is that since the mid-50s, the signal has started to emerge very clearly that the anthropogenic effect is the dominant one. But still, having a study of the solar forcing, and more than that, even the energetic particles, the solar protons that come into the atmosphere and change the chemistry of the middle atmosphere, even the magnetospheric particles that I was talking about a little bit, can all affect this. And so I think good science really dictates that all of those things need to be included in the models, even though we know, or we strongly suspect, that the anthropogenic forcing has been the dominant thing over the last few decades. So I think scientists sort of harm themselves when they say, let's not think about that, let's not include this, let's not focus on this, let's just look at one facet of a problem. Usually that leads to problems and suspicion about the motives of scientists and so on. So I don't personally support that view. And I guess to answer your question more, I think I've answered the question, but I'd say that it's pretty clear in recent times that the dominant effect is more the greenhouse gases that's been dominating the temperature changes in recent times. But even there, I was just at a meeting where this was, in fact, the meeting in China talked quite a bit about this, and there's some real puzzles. The temperatures have sort of plateaued, and so the global temperatures have sort of plateaued and maybe downturned a little bit, and people don't really understand these things, and so these immensely confident statements about we've modeled everything, we understand it all, I think that's quite an overstatement. This is an immensely complex system driven by many different factors, and I don't think we've got all the answers by any means yet.
Thanks. I'm going to steal that answer from now on when people ask me about that.
Okay, good.
Well, thank you so much, Dr. Baker. We so appreciate all
my
your
pleasure.
time,
Thank you.
and this has been absolutely fascinating. I am really sorry that more people weren't here to hear it. I'm glad the recording will be available for them to watch, because they will be. It's fascinating stuff. So thank you so much for buzzing in from where you are in the world to do this for us. And there is interest in seeing more of your slides, if although we also have them here too. So perhaps we can talk about that at a later date. So
Okay. Well, it's my pleasure, and thank you all for listening patiently and for the good questions. And I'm very happy to answer any questions that might occur to you. So just drop me an email line or something. And Dawn, thank you very much for arranging this. It's quite a pleasure for me.
Oh, thank you. This was really enjoyable. I thank you so much for spending time with us today.
Oh, my pleasure, and good luck with all the good stuff you guys are doing.
We also have a Wigio page. It's like an online communication tool, and we'd be happy to set you up with that if you would like to be a part of our group and see the discussions about the sun and about different topics that you may be interested in as well.
Okay, so I hope we'll be in touch about that. Okay.
Sure. Thank you so much.
Okay. Thanks.
Have a safe trip back.
Thanks. Talk to you later.
Bye-bye.
Bye.